In this video, we are continuing our look at the SN1 mechanism, focusing on carbocations. Before we move forward with SN1 reactions, we need to talk about carbocations. But before we talk about carbocations, we need to talk about the transition state of a reaction. So let's consider two reactions and focus on their transition states. Here's a generic reaction where AB reacts with C to form A plus BC. Now let's consider the changes that have to happen. The AB bond has to break while the BC bond starts to form. The AB bond might break more while the BC bond forms more strongly until eventually the AB bond is completely broken and the BC bond is completely formed. Now at the transition state, has the degree of bond breaking equaled the degree of bond forming? That's not likely the case. It's somewhere in between, but how far along the bond breaking versus bond forming has happened depends on the particular reaction. Let's look at a couple of possibilities. Maybe this is the energy of AB plus C, and the products A plus BC are lower in energy. And over here, let's start out with XY plus Z at low energy, and then X plus YZ at high energy. If we think about the reaction pathway, the energy will increase until it reaches the transition state, and then the energy will decrease until it gets back to the products. Over here, the energy will increase until it reaches the transition state, and then the energy will decrease until it reaches the products. Because this transition state is closer in energy to the starting material, it is going to be closer in terms of progress to the starting material. So this won't exactly be symmetric in between these two positions. It would be kind of skewed toward the starting material. This is referred to as an early transition state. Over here, I definitely drew this too symmetric. I'm going to update this. Let's try this again. If we draw it like this, we reach a high point, and then this starts to come back down. Now, here's our transition state. Because it's closer in energy to the product, it's also closer in terms of the time or the progress. And so this would be called a late transition state. Now, why do we want to think about an early transition state or a late transition state? Well, we want to think about the Hammond postulate. This says if two states are similar in energy, they will be similar in structure. If two states are similar in energy, they will be similar in structure. So this transition state is closer in energy to the starting material, and so the transition state will be more similar in structure. So maybe we're looking at something like this, where the bond breaking is only starting to happen, the bond forming is only starting to happen. It's an early transition state that more closely resembles the starting material than it resembles the product. Over here with a late transition state, because the energy of the transition state is closer to the energy of the product, then the structure of the transition state must be similar to the structure of the product. So maybe the transition state then is going to look more like this, where the XY bond is almost completely broken and the YZ bond is almost completely formed. So this structure would more closely resemble the product than the starting material because this state is closer in energy to this state. Why do we care about this? Let's think about another type of reaction where we start out with some starting material and let's say we get to a carbocation, and then that carbocation will react further to give some product. For now, we don't need to worry about the starting material or the product. Let's focus on the carbocation. When we think about the rate of a reaction, we care about the activation energy of the rate determining step. Therefore, we care about the height of the transition state. Well, we can't see the transition state, but what Hammond's postulate tells us is that whatever we can learn about this intermediate, we can apply to the transition state. And then whatever we learn about the transition state will help us to understand the activation energy. And then what we learned about the activation energy gives us information about the rate of the reaction. So we want to learn about carbocations because it helps us to understand the rate of SN1 reactions and many other reactions that involve carbocation formation. So let's talk about some details of carbocations. So a carbocation is a species that has a positive formal charge on a carbon. So for example, we could have a carbon connected to 3 hydrogens with a positive charge. This is a methyl carbocation. We could have a carbon connected to one other carbon that has a positive charge. This is a primary carbocation. We could have a carbon connected to 2 other carbons and a hydrogen. That would be a secondary carbocation. And we can have a carbon that is connected to 3 other carbons and has a positive charge. This is a tertiary carbocation. So methyl, primary, secondary, tertiary, these all exist. If we focus on this carbon compared to the hydrogens and this carbon, for example, it's been shown experimentally that a carbocation is trigonal planar. So that tells us that the carbocation carbon is sp2 hybridized. So what we're looking at then, we have a carbon that has an sp2 orbital, an sp2 orbital going back behind the screen, an sp2 orbital in front of the screen, and then we have a p orbital, which for a carbocation is empty. Right? So these will be involved with bonding to the other hydrogens or carbons, and then we have an empty p orbital. Also determined experimentally, it's been shown that in terms of stability, tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations, which are more stable than methyl carbocations. So let's figure out why. So let's think about carbocation stability. So having a carbon with a positive charge makes it very unstable. So the stability of a carbocation depends on the delocalization of that positive charge. So how can the positive charge be delocalized? One way is to focus on inductive effect. Now, we talked about inductive effect, which can be related to electronegativity, as we were talking about relative acidity. If you have atoms with very different electronegativities, you can say that the more electronegative species is pulling away electron density by the inductive effect. But here we're talking about carbon with carbon or hydrogen with carbon, and so these are very similar in electronegativity. But inductive effect is not limited to big differences in electronegativity. We can also think about polarizability. Because hydrogen is such a small atom, its cloud of electrons is not very polarizable. So this carbon-hydrogen bond is not very polarizable. So here, carbon is saying, I have a positive charge, somebody help me. And these guys are trying to help out, but they can't really do much. So maybe this hydrogen is going to share this much electron density. You can't even tell. So this is a little bitty arrow with a positive on the backside. So there we go. That's how much help hydrogens can give. So what the carbon feels, instead of feeling the full positive charge, it probably feels a big partial plus. So doesn't really help that much. Next, we have a primary carbocation because the carbocation carbon is connected to one other carbon. The hydrogens still aren't helping very much, right? Itty bitty bitty amount of electron density being released by inductive effect, but carbons, because they are bigger, they're more polarizable. And so this bond is more polarizable. And so this carbon can release more electron density to the carbocation carbon. So with only one carbon releasing electron density, maybe here we're looking at a partial plus that's a little bit smaller, and so there's a little less positive character on the carbocation carbon. With a secondary carbocation, this hydrogen is helping just a teeny bit, but we have two other carbons that are releasing more electron density to the carbocation carbon. So maybe here we end up with a smaller partial plus because this carbon's taking on a little partial plus and this carbon's taking on a little partial plus as well. Finally, in the case of a tertiary carbocation, we have three carbons that are releasing some electron density to the carbocation carbon. So with all these guys helping out, the carbocation carbon probably feels more like a little partial plus because all of these other carbons have taken on a partial plus as well. So I'm trying to represent the size of partial positive. How much positive character does it have based on the size of my delta plus? So here, this carbocation carbon, even though it has a formal charge of +1, it feels a small partial plus because that's spread out around all the carbons by inductive effect. Over here, this carbon, which has a positive formal charge, because hydrogen can't help that much, this carbon must feel almost a full positive charge. It would be a huge partial positive charge. So in terms of carbocation stability, tertiary carbocations are going to be more stable than secondary, more stable than primary, which are more stable than methyl, because the positive charge can be better delocalized by inductive effect. Now, the second way that delocalization of a positive charge can occur is through something called hyperconjugation. Hyperconjugation. So here we're talking about the delocalization of charge by orbital overlap with an empty p orbital of a carbocation. So let's say we're talking about, here's our carbocation, and here is the empty p orbital. If this carbon is bonded to a hydrogen, so this would be one of the sp2 orbitals is overlapped with a hydrogen, or if a carbon was bonded to another carbon, this carbon is connected to something else, a hydrogen, for example. Between the carbon and the hydrogen, this is the only set of electrons. These are perpendicular to the empty p orbital, so they can't help out. So there's no hyperconjugation between a hydrogen that's directly connected to the carbocation and that p orbital. But over here, it's not the bond adjacent, but the next one after that. This bond can line up with the p orbital, and it can basically dump some electron density into the empty p orbital. So this very vague idea of dumping electron density through space into an empty p orbital, this is hyperconjugation. So if we look at our methyl carbocation, we have 0 options for hyperconjugation. If we look at our primary carbocation, remember these bonds are all perpendicular to the p orbital, so they can't help, but this bond, and this bond will all be like this. And so they can be parallel to the empty p orbital. So a primary carbocation has 3 possibilities for hyperconjugation, or 3 bonds that can donate just a teeny bit of electron density. When we're looking at a secondary carbocation, and this bond doesn't help, but this bond, this one, and these three can all donate electron density by hyperconjugation. So in a secondary carbocation, we have 6 bonds that are able to donate, and in a tertiary carbocation, we have 9 bonds that are able to contribute. So once again, this tells us that tertiary carbocations are more stable than secondary, which are more stable than primary, which are more stable than methyl, because there are more options for hyperconjugation to delocalize the positive charge. So here we have electrostatic potential maps that represent our methyl carbocation, a primary, secondary, and tertiary carbocation. With electrostatic potential maps, red is negative and blue is positive. So here you can see a lot of positive character around the carbocation. Here we still have a lot of positive character, although it's more spread out. Here there's less positive character because it's more spread out. And in the case of this tertiary carbocation, there's a lot less positive character because that charge is distributed so effectively throughout the neighboring carbons as well. So carbocation stability, tertiary carbocations are more stable than secondary, are more stable than primary, are more stable than methyl carbocations because of both inductive effect and hyperconjugation. Understanding this trend in carbocations is very important because a carbocation is an important intermediate in many different types of reactions.